Hi, this is our data mining group assignments video assignment. We are from Group07. I'm the group leader Jun Qin. This is my group member Luo Kan Yong.
Hi, my name is Luo Kan Yong. Today we will walk you through our comprehensive analysis of the accidental drug-related death dataset. Our primary objective is to uncover hidden demographic vulnerabilities, predict specific outcomes based on drug usage, and identify highly anomalous fatality cases.
And before we dive into the technical implementation, I will outline our work breakdown structure to clarify how we divided the responsibilities for this project to ensure accountability and autonomy. For the data preparation phase, I handle the data pre-processing pipeline, including handling missing values, temporal extraction, and feature transformation. In terms of algorithmic implementation, I was responsible for developing the predictive linear regression model and the anomaly detection model using isolation forest. Finally, I handled the interpretation of the resourcing visualization.
And I conducted the initial exploratory data analysis. I was responsible for implementing the classification model using random forest and the clustering model using k-means. I also handled the extraction and the evaluation of the validation metrics such as accuracy and silhouette scores.
Now, let's briefly look at how we prepare our data for the machine learning algorithms. As you can see here in our Python script, raw data requires rigorous cleaning. First, we dropped duplicate records. For the age column, we utilize simple inputter with the medium strategy to handle missing values without allowing extreme outliers to skew our central tendency. Because machine learning algorithms require numerical metrics, we transform the categorical drug variables. Because machine learning algorithms require numerical metrics, we transform to categorical drug variables like heroin, cocaine, and fentanyl from white and null strings into binary indicators, using a lambda function to convert them into 1 second and 0 seconds. Finally, to ensure distance-based algorithms operate efficiently, we scaled our continuous variables using standard scaler. With our clean data set ready, I will now pass it back to Luo Kan Yong to demonstrate our first two data mining techniques.
Thank you. Our first problem was understanding demographic vulnerabilities. Specifically, we wanted to predict the victims' gender based on their age, the year, and the combination of drugs involved. We selected the random forest classifier because it is highly robust against overfitting and handles binary drug filters exceptionally well. Look at the code. After our train test split, we initialized random forest classifier with 100 estimators. We then fitted the scaled training data. To evaluate our model, we extracted several metrics. Our model achieved an accuracy of 0.6548. To ensure this wasn't due to overfitting, we ran a 5-fold cross-validation, yielding a very stable mean accuracy of 0.6688. As you can see in Figure 1, the confusion matrix visually summarizes this. The model successfully classifies the majority class, which is male but struggles slightly with the minority classes. This interpretation tells us that while gender prediction based on drug usage patterns carries inherent challenges, our algorithm performs significantly better than a random baseline, proving that distinct behavioral patterns do exist between genders. Next, we implemented unsupervised clustering. Without predefined labels, we wanted to see if the algorithm could identify distinct high-risk demographic clusters. We utilized k-means, configuring it to find 3 clusters based on age and drug involvement. For evaluation, we calculated the silhouette score, achieving a 0.2508. Let's interpret what this means using figure 2 or box plot analysis. The positive silhouette score indicates that while human demographics naturally overlap, the k-means algorithm successfully mapped distinct centroid profiles. The box plots clearly shows the variance in age distribution across the 3 clusters. This insight is highly valuable for public health officials, proving that we can algorithmically segment victims into distinct generational risk groups, such as younger experimental users versus older chronic users.
Thank you. Now I will demonstrate our predictive regression and anomaly detection models. As you can see here in our Python script, for our predictive modeling, we wanted to scientifically test the hypothesis. Is there a linear correlation between the specific types of drugs a victim consumes and their exact age? To test this, we implemented a multiple linear regression model. As shown in the code, we isolated the target variable age and fitted the linear regression algorithm against the drug and temporal features. The evaluation of this model is highly insightful. We achieved an R-squared score of 0.0645. While this number is low, mathematically, this is a critical finding. It empirically demonstrates that the relationship between a victim's age and the type of drug consumed is strictly non-linear. This interpretation here is that drug abuse is an universal crisis. It permeates all age demographics without a simple predictable linear progression. We cannot simply bind a specific drug to a specific age group. Finally, we utilize the isolation forest algorithm for anomaly detection. Traditional statistics often miss extreme edge cases. We configured the algorithm with a contamination rate of 0.05, mathematically instructing it to isolate the top 5% most extreme statistical outlier in our dataset. It permeates all age demographics without a simple predictable linear progression. We cannot simply bind a specific drug to a specific age group. The algorithm successfully isolated 596 anomalous cases out of nearly 12,000 records. Let's look at the figure 3. The anomaly scatter plot. The dense blue baseline represents the standard sociological trends over the years. The red dots scattered away from the center represent the 596 anomalies. The interpretation of this is powerful. These red dots graphically highlight victims who suffered fatal overdose under statistically extreme conditions, such as unprecedented youth, extreme old age, or highly unusual multi-drug interactions. By isolating these 596 cases, we provide a highly targeted focus list for medical examiners to study the most extreme fatal overdose events.
To conclude, our data mining project successfully extracted actionable insights from a highly complex sociological dataset. By applying a diverse set of algorithms, we moved beyond the basic statistics to understand the deeper mechanics of accidental drug-related fatalities. First, we mathematically proved the non-linear nature of drug abuse through our multiple linear regression model. The low R-square score is actually a critical finding. It tells us that substance abuse is a universal crisis that does not neatly track with age in a straight line. It proves that no single age demographic is immune. Second, we identified stable gender-based vulnerabilities using the random forest classification, proving that while human behavior is inherently unpredictable, underlying patterns do exist and can be modeled. Third, we successfully segmented risk groups via k-means clustering, providing distinct generational profiles that can help authorities tailor their intervention strategies rather than using a one-size-fits-all approach. Finally, we selected 596 critical medical edge cases using the isolation forest algorithm. Instead of being overwhelmed by nearly 12,000 reports, medical examiners now have a highly targeted list of extreme anomalies to investigate further. Moving forward, fusion improvement could involve using advanced ensemble models like XGBoost or applying natural language processing to extract text features.
Before we sign off, it is absolutely vital to address the ethical considerations and limitations of our data mining process. Working with mortality data carries a heavy moral responsibility. First, regarding data privacy, although our dataset was technically anonymized, we must acknowledge the critical risk of re-identification. If someone were to maliciously combine specific fields like death city, date, and exact age, they could potentially trace these records back to real individuals and grieving families. We must ensure this kind of data is stored securely and never exploited. Second, there is the crucial issue for algorithmic bias and fairness. Machine learning models trained on historical data can inadvertently learn and amplify existing societal biases. We must handle our predictive models, especially our classification and clustering results, with extreme care to avoid unfairly stigmatizing specific demographic groups, minority races, or local communities. We must never use clustering algorithms to apply harmful or discriminatory labels to vulnerable populations. Lastly, there is the principle of responsible use. Data mining in this context should never be weaponized for punitive law enforcement actions. The analytical insights we mine today must be used strictly for proactive public health improvement, targeted harm reduction programs, and the equitable allocation of medical resources. At last, we would like to take a moment to express our most sincerely gratitude to our instructors. A special thank you goes to our lecturer, Dr. Ambisa Van Sangodian, for delivering the fundamental theories and providing continuous, insightful guidance throughout this module. We would also like to extend our deepest appreciation to our practical tutor, Mr. Jeff Edward, for his invaluable technical support, hands-on advice, and immense patience during our weekly lab sessions. Your combined mentorship made the successful completion of this project possible. This concludes our data mining group video assignment. Thank you very much for your time and attention.